And what would be happening here is that the universe itself would be going around the Earth on what they call a sidereal rate. That's 23 hours, 56 minutes, 4.1 seconds. The universe goes around the Earth, okay? Okay, so let's just see how this can play out. Let's put Mars in the center. And if you compare this to the heliocentric view, where this every distance you see here, every motion, every position will be exactly the same. The only thing we've done is change centers. Now, I'll show that to you in a second. Okay, so let's stop this side and let's go to the orrery. I mean the geocentric. What's that? Okay, so here we are. Here's the heliocentric. Here's the geocentric. The sun is in the center here. Earth is in the center here. Now notice the sun and Earth are straight up and down there. They're straight up and down. Here's Mercury, same position. Okay, everybody see. Stop it for a second. Okay, look, see, everything's exactly the same. Mercury's here, Mercury's here. Mars is here, Mars is here. Earth is here, Earth is here. Venus is here, Venus is here. Just like a clock. Okay? Let it go. Watch them all keep the same position. So now you know why they say that either one could be correct. Okay.
So the observable positions, if I'm looking at them, are sure to be the same.
Yeah. Either system.
So they picked the one without God.
That's right. They picked the one without God, yeah. That's a good way to put it. Now, God could have made this one too, if He wanted to. And we would still worship God all the same. Okay? If that's what Scripture had told us.
But also the Scriptures would have had to say that the earth is moving.
Right. But it doesn't. All the Scriptures say the earth doesn't move, and they all say the sun moves. Now, what are you going to take away from that? Especially now that you know that both systems are possible. Okay? All right, so let's go on to that next Ptolemy, Copernicus, Tycho. Yeah, I think it's called geocentric something. Oh, there it is, yeah. Okay, so now here's Ptolemy's model. Ptolemy was an astronomer, Greek astronomer, lived in Egypt around the 2nd century AD, and he created this model, and he had what we called epicycles, okay? The planets would go around epicycles, and he tried to basically make a diagram that worked from what he saw in the sky. Okay? But he wanted to keep Earth in the center. And his model was pretty good. Pretty accurate. The only problem is he got Mercury and Venus in the wrong place, and it messed up his system. Okay? So Galileo came along and said, you know what? Ptolemy's system doesn't show us the phases of Venus, and we can see the phases of Venus from Earth with our telescopes, with our new telescopes. Venus has phases as we look at it, just like the moon has phases. Quarter, full moon, half moon, whatever. Okay? But Ptolemy's model wouldn't allow the phases of Venus because he put Venus in the wrong place. But he was smart enough to say, you know what? I don't know how far away Venus is, so I'm going to make it a variable. And he put 6 variables in his model so that someday in the future, when someone figured out what the true distances were, they could put it back into his model and make it work right. And guess who that was? That was this guy named Tycho. Okay? Let's put Tycho up there. Now, you're going to see a subtle change. You're going to see that ring disappear and another ring appear. And that's basically all that Tycho did. Everything has to be exactly the same, remember. They can't be moving in different directions in each model. They all have to be the same. It's just the way that they do it. And so Tycho fixed Ptolemy's model, and it works. That's the one that Newton said would work. Okay? And Einstein said would work. All right, so let's go to the Copernican model here. See? Everything's exactly the same. If you put the Tychonic and the Copernican side by side, you'd see exactly the same thing. You'd just see different circles. Because the circles represent how they made them move, not where they moved. Okay? All right. So let's go back to the PowerPoint. Now, there are many more animations on this CD that I am not going to show you tonight because we don't have time. Okay? But one common question that comes up is, well, how does the geocentric system explain the seasons? How does the heliocentric system explain the seasons? What were we taught in third grade? Well, we were taught that the Earth is on a tilt, a 23.5-degree tilt, okay? And that it goes around the sun. And because it goes around the sun's going to hit the Earth with its light in different ways because the Earth is moving, okay? The geocentric system says, no, the Earth is straight up and down, and the sun is moving up and down. Okay? So the sun's going to move up 23.5 degrees and down 23.5 degrees. So in essence, it's going to be making a spiral around the Earth. And what's making the sun do that? The universe that's going around. It's carrying it. And the whole universe itself is moving up and down just a little bit, up and down, over the course of a year, and it's moving the sun with it. And you'll see the stars will move as well. Okay? So that's how, but I can't show you that right now. It's going to take too long to bring it up. So next slide. There's this other thing called stellar parallax. Now, in Galileo's time, he said, well, if my theory is correct, then we should be able to see stellar parallax. And what this is if you got two stars and you looked at them from Earth, they're going to look they're going to form an angle. And if the Earth goes around the sun, it's over here, then this angle is going to change. This star is going to be over here this time. Okay? That's called parallax. Two different stars you're looking at, and you can even do that with your thumb. If you put your thumb out like this and you close one eye, okay? And then you open the other eye, and you close this eye, what's going to happen to your thumb? Try that. Put your thumb out in front of you. Okay? Your thumb looks like it's changing position, right? Okay, that's parallax. And the distance between your eyes is what? 4.2, I forget what it is, but is the same thing as the distance between the Earth here and the Earth here. This is your one eye here, this is your other eye here, to give you an analogy of how that would work in space, okay? And so the claim was, well, since we discovered stellar parallax in 1838 by Frederick Bessel, well, that just proves heliocentrism. Because obviously the only way to explain that is to have the Earth look at the star here and the Earth look at the star here, and we see the parallax that we normally see in the sky. And then someone said, you know what? The geocentric system can do the same thing. If you turn the stars in the sun around a fixed Earth, you're going to see exactly the same angle that you see in the heliocentric system. Okay? Next slide. There was another stellar phenomenon called stellar aberration. And if you look at any star in the sky and you watch it over the course of a year, that star will make a little circle like this. Every single star in the sky makes a little circle, and it makes the same size circle no matter how far away the star is or how close it is. No matter whether it's up here or over here, it makes this little circle. It's called stellar aberration. And the big thing was, well, the heliocentric system can explain that because the Earth goes around the sun. But then somebody figured out, well, the same thing would happen if the stars went around the Earth. You'd see the same exact thing. And those animations that I gave you on the CD-ROM will show you that. You can go look at it yourself. Okay? Next slide. The Foucault pendulum. Has anybody ever been to a museum and seen the Foucault pendulum? Okay? And what's one of the first things that you see when you go in to see the pendulum? You see a plaque there that says, this proves that the Earth rotates on an axis. That's what you'll see. So they basically brainwash you before you actually see the pendulum and find out what's really making it tick. Okay? But what did Mach tell us? Mach told us that you're going to get the same effect in that Foucault pendulum whether the Earth is fixed and the universe goes around it, or the universe is fixed and the Earth rotates within it. Why? Because the same forces are going to be created. Look at this. Okay? Same thing. It's just a relative position is all it is. Okay? And if that's the case, if it's just a relative position, then the same forces are going to be created to make that pendulum swing. Okay, next slide. And of course, we have the bulge of the Earth. I was going to go through that, but we don't have time. Another issue was the retrograde motion of Mars. They said they can only see it. But what Mars does is you look at it in the sky over the course of a few months, and it'll go like this, if you watch it, and then all of a sudden, it'll start to go backwards in the sky. It's an amazing phenomenon if you watch it over the course of, say, 3 or 4 months. And then it'll stop again and start going back the other way. Now, is Mars really doing that? No. Mars is just moving. It's just moving. It's just the way we look at it from Earth. Okay, that's going to change the angle because Mars moves slower than the Earth in the heliocentric system. But you're going to see the same exact thing in the geocentric system. Okay? And you'll see that on the animations. Okay, next slide. There was an experiment done by this man named Airy. Too complicated to get into now because I think I'm overloading your brains, so I'm just going to skip this one, and I'm going to leave that to you to go look at the CD. All right, next slide. Keep going. Okay. Now here is one of the most famous physicists in the world in the late 1800s, a contemporary of Einstein. He knew Einstein very well. As a matter of fact, he collaborated with Einstein on the theory of relativity. Okay? His name was Hendrik Lorentz, a Dutch physicist. And all those things I just showed you, stellar aberration, stellar parallax, all those things, this is what his conclusion was. Briefly, everything occurs as if the Earth were at rest. That was his conclusion. That's the best way to explain all those phenomena I just showed you. One of the most famous physicists in the world. Okay, next slide. And so this just laid the groundwork for one of the most famous experiments the world has ever performed. Happened in 1887. Have you ever heard of it? Called the Michelson-Morley experiment? Anybody? A couple? Okay. Well, everybody said, you know what? We really need to find out whether the Earth is moving or not. Because we had all these experiments taking place in the 1800s that I haven't even shown you here. A guy named Dominique Arago from France found the Earth wasn't moving. We saw Airy in 1871, whose conclusion was that the Earth wasn't moving. We just saw Lorentz say that in regards to stellar aberration and stellar parallax, it appears as if the Earth is at rest. So let's do a definitive experiment to find out what's really going on out there. And so they devised this very unique experiment. And what they did was they got light beams. And they shot these light beams perpendicular to each other. And the idea was, if the Earth is going around the sun, okay, and we shoot one of those light beams in the direction that the Earth is going around the sun, and then we take another light beam and we shoot that straight up so that it's not affected by the motion of the Earth, then we should have a difference in those two light beams, in the speed of those two light beams. Why? Well, because if we shoot this light beam, if I shot this light beam, you see it's reaching that wall over there, and I put water in front of it, it's going to take a longer time to reach the wall because it has to travel through a medium. So if this light has to travel through a medium, it should take a longer time than this light that's really not traveling against the medium because the Earth isn't moving up and down. According to the heliocentric view, it's going around, going laterally. Okay? Does that sound reasonable? Yeah, sounds reasonable. All right, next slide. So here's the expected results. If the Earth were moving around the sun, we would expect that the yellow beam would be slower than the red beam, and we would get this kind of wave pattern. Okay? The red beam would be ahead of the yellow beam. And they knew exactly the distance that those beams should be apart if the Earth was indeed moving around the sun at 19 miles per second, which it would have to do if it's going to complete its journey in 1 year. It has to go 19.5 miles per second, or 30 kilometers per second. And they could tell you, because they knew how light worked, they could tell you exactly the distance between these two waves that should be if the Earth was indeed moving around the sun. And what did they find? That's what they found. The waves were almost identical. Okay? Almost identical. So what does that tell you? Well, here's one possibility. The Earth ain't moving. Because if it was moving, then you would see this. But we see this. Okay? And the whole world was in consternation. What are we going to do with this experiment? Here we wanted an experiment to show us definitively that the Earth was moving around the sun, and what it comes back and does is it tells us that it's not moving. Okay? Next slide. So here's Michelson's report in the American Journal of Science, 1887, explaining, what had happened. The results were not what he expected them to be. You can read that on your own. Next slide. Here's a letter that Albert Michelson, right here, this is his actual letter. I went to the microfiche files at the University of Maryland to dig these things up, copy them for you, and here they are. This was written in 1891. He's writing to Lorentz, because Lorentz, remember the Dutch physicist who said that it appears that everything is as if the Earth is at rest? Well, he knew Michelson did his experiment. He says, what's going on here? And Michelson writes to him and says, I don't know what's going on. That's basically what his letter says. I can't explain it to you. I can't explain my own experiment to you. I expected my experiment to show that the Earth was moving, and it shows that it wasn't moving. All right, next slide. And so Lorentz then writes to Lord Rayleigh, another famous English physicist, and here's his actual handwriting. You see it's a little different than Michelson's. And he says, over here, he says, could it be that Michelson made a mistake in his experiment? Because I don't know how to explain this. Okay, next slide. And here's the actual English version of his, he says, can there be some point in the theory of Mr. Michelson's experiment which has yet been overseen? Did he miss something? Did he leave something out? Please help me. Next slide. All right, here's an historian, Bernard Jaffe, writing on this experiment. Here's Michelson himself. The title of the book is Michelson and the Speed of Light. And he says this, the data from Michelson's experiment were almost unbelievable. The so-called ether wind had no effect whatever on the velocity of light, whether the beam was traveling with the wind or across it. There was only one other possible conclusion to draw, that the earth was at rest. This, of course, was preposterous. Okay, next slide. Here's another one, written in 53, I think. Relativity for the Layman, written by James Coleman, another famous physicist. He says, the easiest explanation of Michelson-Morley was that the earth was fixed in the ether and that everything else in the universe moved with respect to the earth and the ether. Then we on earth would not experience an ether wind, thus making the detection of the ether impossible. Such an idea was not considered seriously, since it would mean, in effect, that our earth occupied the omnipotent position in the universe, with all the other heavenly bodies paying homage by moving around it. So, talk about philosophy. Remember we talked about philosophical bias? Okay? Well, we just can't have that. You see? So we think these men in white lab coats are all very honest, and some of them are. Okay? But when science rubs up against their philosophical biases, yeah, there's a lot of twisting that goes on. And this was one of them. Okay? Next slide. This was written by another physicist, G.J. Whitrow, in 59, I think this was, Structure and Evolution of the Universe. He says here, it is both amusing and instructive to speculate on what might have happened if such an experiment, that is the Michelson-Morley experiment, could have been performed in the 16th or 17th centuries when men were debating the rival merits of the Copernican and Ptolemaic systems. The result would surely have been interpreted as conclusive evidence for the immobility of the earth, and therefore as a triumphant vindication of the Ptolemaic system and an irrefutable falsification of the Copernican hypothesis. Now that's a physicist telling us that. Okay? So if the Pope who chastised Galileo had the Michelson-Morley experiment, it would have been a slam dunk. All he would have to do is show Galileo, see, this experiment says the earth doesn't move. And the case would have been over. There would have been no tortures, no long, drawn-out drama at all. All right, next slide. Here's Lorentz writing again to Fitzgerald, another Dutch physicist. Actually, he's a physicist from Ireland, very famous physicist of his day. And so these guys are kibitzing back and forth about how they're going to explain away the Michelson-Morley experiment. What can we do? And so they devise this scheme that says, I know, what we'll do is we'll say that the reason that yellow wave is really close to the red wave is that Michelson's apparatus, the experimental apparatus that he used, shrunk just enough to make those waves coalesce instead of being spread apart. That's what these guys are writing. These are grown men now, okay? All right? Next slide. And so what we have here is the contraction theory, that when matter moves, it contracts. And just enough to hide the fact that the earth seems to be still in space. Okay? So if we contract the apparatus, what that will allow us to do is to go back to this thing here. Okay? I'm sorry, it will allow us to keep everything, in other words, we will be able to explain why there was a coalescence of the waves and not this. Next slide. Oh, we'll go back to that slide for a minute. And he actually put it in an equation. The new length, that's length prime, equals the old length times this equation here. 1 minus v squared over c squared. V squared is the velocity the earth is going. C squared is the speed of light. And since we squared them, we have to get the square root of them, and that's the formula that we're going to use. very convenient formula, just an ad hoc formula. Nobody knew whether it was right or wrong or indifferent, but it worked to make it appear that the apparatus shrunk. Next slide. Now, Albert Einstein came along, okay, and he says in 1924, soon I came to the conclusion that our idea about the motion of the earth with respect to the ether is incorrect, if we admit Michelson's null result as a fact. This was the first path which led me to the special theory of relativity. Since then, I have come to believe that the motion of the earth cannot be detected by any optical experiment, though the earth is revolving around the sun. There's a great scientist for you. I believe the earth is going around the sun. I can't tell you why, but it's true nevertheless, you see. All right? That's what he's telling us. All right? So basically all he can say is, well, I guess we'll just have to throw up our hands and say, we can't prove it by any experiment, but we really do know that it's the truth. Next slide. So in 1971, a biography is written about Einstein, and here it talks about the Michelson-Morley experiment. It says here, in the United States, Albert Michelson and Edward Morley had performed an experiment which confronted scientists with an appalling choice. Designed to show the existence of the ether, at that time considered essential, it had yielded a null result, leaving science with the alternatives of tossing aside the key which had helped to explain the phenomenon of electricity, magnetism, and light, or of deciding that the earth was not in fact moving at all. Okay, so they knew what the choices were. Choice A was the earth isn't moving. Choice B, well, we know that Lorentz said there's a contraction of the apparatus because the earth and the apparatus are moving against this ether stuff out in space. Okay? Next slide. Here's another part of that same book. After the Michelson-Morley experiment, there seemed to be only three alternatives. The first was that the earth was standing still, which meant scuttling the whole Copernican theory and was unthinkable. Okay? Philosophy, yeah. Unthinkable. Now think about it. Why would it be unthinkable? Well, remember what we covered in the first part of the lecture? Because if the Bible's true, when it says that the earth doesn't move, what does that do for the rest of society? What does that do for the church who stuck up for it? What does that do for the atheist who now finds out, wow, the earth is in the center of the universe? You mean I can't escape somewhere out there in the recesses of space and pretend that I don't exist? I actually have to be answerable to God? That's what it does. That's why it's unthinkable. You see? Because Copernicus made us all safe. He took us out from the center, so we didn't have to worry about all that stuff. Okay? I can go on and live my life the way I wanted to because I got rid of God. God is dead, you see. But now God's very much alive. He's knocking on the door. Knock, knock. See this experiment I just gave you, Michelson-Morley experiment? And didn't I give you a couple other experiments before that? George Airy and Dominique Arago and stellar aberration and stellar parallax. You got them all explained from the geocentric point of view. I'm giving you all the answers you need. You just keep running away from it. And now you've come up with this absurd theory that when matter moves, it shrinks. And just enough to hide the motion of the earth to make it look like it's standing still. Wow, you guys are too much. I can just see God saying that. I really can. Okay. So Einstein had a choice. Admit the earth is not moving through the ether, or get rid of the ether and say the earth is moving, but we can't detect it. Now, why did he want to get rid of the ether? Well, because he realized that Lorentz's idea that there would be a contraction of matter if ether if the Earth was moving through the ether, isn't going to work. The reason why is because this ether out in space was previously thought to be without friction. That the planets could move without friction and they could go the speed they wanted and not be impeded in any way by this ether. So that was the idea of ether. But now Lorentz is coming along and saying, well, no, the ether does have some friction. It actually has enough friction to contract matter in Michelson's experiment to make it look like the Earth is standing still. And I said, you can't do that. Because there is no proof for that. You're just making an ad hoc assumption. Okay? But Einstein still needed Lorentz's theory that matter was shrinking. Because that's the only way you can explain the Michelson-Morley experiment, you see. The only thing he disagreed with was how Lorentz got to that shrinking. So Einstein had to come up with another theory. And what do you think his theory was? It just happens. It just is. It's a principle of nature. We can't explain it. It just is. As a matter of fact, during his day, Einstein was accused by many philosophers of violating the metaphysical principle of cause and effect. Because he was saying there was an effect without a cause. And if you're a scientist, you don't have effects without causes. All of science is built on effects that are made from causes. But here's the greatest scientists in the world telling us, well, we can't explain it. We know it has to be true. It has to be true that there is a shrinkage of the apparatus. Because why? We know the Earth is going around the sun. We know that has to be the case. Okay? And let me tell you this, Einstein was virulently anti-Christian. Okay? So if you don't want God in the equation at all, yeah, you're going to try to find some way out of this problem, even if you have to violate your own science to do so. You violated the principle of cause and effect. Okay, next slide. He says in his book, if Michelson-Morley is wrong, then relativity is wrong. Translation, if someone proves ether exists, my relativity theory is totally destroyed. So he got rid of the ether because he's told Lorentz it wouldn't work. He made up this idea that you can have a cause without an effect. And he says, if you can prove that ether exists, then I'm totally through. I don't have any answers for you. Okay? Next slide. And one of his greatest opponents, Charles Lane Poore of Columbia University, physicist, PhD, said, if it should develop that there is a measurable ether drift, then the entire fabric of the relativity theory would collapse like a house of cards in a second. Next slide. Here's all the guys that found ether after Einstein. Okay? All of them. You ever hear about any of those guys? Nope. You might hear one or two of them. Okay? Next slide. There was a guy, Dr. Miller, Dayton Miller, who did experiments. Michelson-Morley did 36 trials in their experiment in 1887. This guy did 100,000 trials just to make sure he got it right. And every time he did the experiment, what did he get? The same ether that Michelson-Morley got. Okay? Next slide. And so Einstein hired this guy named Robert Shanklin to discredit Miller and his results. And so Shanklin went in there to check on Miller's results, and he said, well, it seems to be a heat problem here. Because if you have heat in any of these very sensitive experiments, it could foil the experiments. Okay? And Miller said, there's no heat problem here. Okay? At least nothing negligible enough to distort the experiment. But just in case, I'm going to do them all over again. and we're going to fix the heat problem. Okay? So that's what he did. And what happened? Well, Shanklin ignored all those experiments where the supposed heat problem was taken away. Why? Because he was enamored with Albert Einstein. Because Albert Einstein had saved the world from having to go back to the Christian dogma that the earth was in the center of the universe. I mean, you don't want to mess with that. Okay? All right, next slide. Now, we have a whole thing in the DVD on Michelson Morley experiments. So everything I'm telling you and more is available in that DVD for you. And this is 40 minutes long. So I go into every little nook and cranny of it so you can have all the information in front of you. And again, it's not me telling you this. I'm just the spokesman. I'm not making this up. I get all the information I'm telling you from the very scientists who examine these experiments, okay? And I'm just bringing it to you. All right, next slide. Next slide. This, the GPS. Yeah, let me go through this. What time is it, by the way? How much? 6 to 9. When are we supposed to end?
That's road. So we want to leave some room for questions. So
yeah, leave a room for questions. Yeah, okay. So 10 o'clock, is that reasonable or?
9:15, you're going to be wrapping up about 9:30.
Is that right? Okay. All right. So let me just touch upon this. No, wait a minute. Actually, what we should do, because they can look at this in the DVD, let's keep going forward until I tell you to stop. Keep going. Keep going, keep going. Just keep clicking. Okay, stop here. Go back a little bit.
One more?
Yeah. Go back another one. Okay, right here. All right, let's just shift gears here a little bit, okay? Let's talk about what they were beginning to see in their telescopes around the 1920s and 30s, okay? This guy, Edwin Hubble, he's the guy that the Hubble Space Telescope is named after, okay? Very famous astronomer. He looked out in his telescope for the first time from Mount Wilson. First time in history. Somebody was able to look at it through a telescope at the distant galaxies. Can you imagine how he felt? Seeing all these little spiral galaxies and everywhere. But what he found was something that he just didn't like. Every galaxy that he looked at, north, south, east, west, sideways, backwards, whatever way he looked, he saw all these galaxies had one particular feature. And they were all redshifted. Now, that doesn't mean much to you. When you see a sunset, the sun is redshifted. Okay? When you see it overhead at noon, there's no shift. You just get that pure light. Okay? But the light is magnified when it comes through us to us at the sunset, so we see red in the sun. Okay? And that's because the wavelength of the light is stretched a little bit, and you'll see red. If it's shortened, you'll see blue. All right? What he saw in every galaxy that he looked at was red. And he said, that's peculiar, because that puts us in the center of the universe. Because if I wasn't in the center, what I should see if I looked over here is blue, and there blue, and maybe over here red, and there red, but I shouldn't see red everywhere. I shouldn't see the same symmetrical pattern. But he did. Okay, so what did he say? Next slide. Such a condition would imply that we occupy a unique position in the universe, analogous in a sense to the ancient conception of a central Earth. The hypothesis cannot be disproved, but it is unwelcome and would be accepted only as a last resort in order to save the phenomena. Therefore, we disregard this possibility and consider the alternative, namely a distribution which thins out with distance. That's another topic, but look at that emotional reaction he has. We just can't accept this. Okay? Haven't we seen that over and over again? Okay? philosophical bias to the scientific evidence. What?
Like a trend.
Yeah, a trend. All right, so there we have it, okay? So what did he do? Well, you thought Lorentz's shrinking of matter was kind of weird, and Einstein say the shrinking happened, but I don't know, can't tell you why? You think that was weird? Well, look what this guy does. Next slide. Oh, by the way, here's Stephen Hawking saying the same thing. He basically says, if we see red everywhere, that means we're in the center of it all. Okay? Next slide. Next slide. Okay, so go back one slide. So Hawking comes up with a ingenious proposal here following Hubble. Hubble was the first one to think of this. Hubble says, okay, let's do this. You know this big ball that we're all talking about where we see the red everywhere? Well, let's just take the center out of it. We'll just suck all the air out of this balloon, or out of this ball, and we'll take all the matter out of this ball, and we'll just make it a balloon surface. So there's nothing in the center anymore. We're just little dots on the surface of a balloon. And if I blow up that balloon, it's going to get bigger. And what it's going to do is all the galaxies that are on that balloon, they're all going to be spreading out. They're all going to be spreading out. And when I look at them, if I'm on this galaxy here and I look at this galaxy over here, what am I going to see? I'm going to see a redshift. And if I'm on this galaxy here and I look at this galaxy here, what am I going to see? Redshift. Okay? So you see what they did? They didn't like the Earth being in the center, so they took the center out. And they put us on the surface of a balloon. Did you ever hear this thing called the Big Bang? Well, that's what that was. You see, if you have a big explosion and you want to get rid of the Earth in the center, well, you just put all the galaxies on the surface of that explosion. And as it keeps exploding, it's expanding out. It's Big Bang, expansion of the universe. We've heard of that, the universe expanding. That's why they created it. Because they put the galaxies on the edge of that expansion, and all we can see now is redshift. And that's the explanation for redshift. When the easiest explanation is that we are actually in the center. And that's why Hubble saw the redshift everywhere in the galaxies. Okay? All right, so let's cover one more topic, and then we'll call it a night. Keep going. Keep going. Keep going. Okay, let's stop right here. Go back one slide. In 1963, these two gentlemen named Penzias and Wilson, anybody ever heard of them before? Okay. They, by accident, discovered through their telescope, radio telescope, the cosmic microwave background radiation. This is a microwave, like your microwave oven, okay? Those microwaves basically are all around us, and they come from every place in the universe. It's ubiquitous, okay? Very slight, but we can measure them. They're only 2.75 degrees Kelvin for heat temperature of the energy they create in being waves, but they're there, okay? So they discovered this, and everybody said, oh, I know where that comes from. That comes from the Big Bang. Yeah, because when the Big Bang first started, it was 3,000 degrees Kelvin, and then after billions of years, it began to cool as it expanded, and so now it's 2.75 degrees Kelvin. That's where it's all coming from. It had to fit like a glove, you know? It was just remarkable. They really thought they had won the war. And then in 1978, people began to say, well, you know what? If you actually look at that microwave radiation out there, it's not smooth like it should be. It's not equally distributed like it should be if you had an explosion. Because an explosion has to go symmetrical everywhere, and you have to have a homogeneous, like homogenized milk. Okay? But what they found was that this microwave energy out there wasn't like homogenized milk. It was more like lumpy milk that we used to get in the bottles. Okay? It was lumpy everywhere. And here are the lumps. See those different colors there? Lump here, lump here, lump here, lump there. These all were different temperatures of the microwave radiation. Very slight differences, but they were still differences. Okay? So it wasn't good for the Big Bang, because the Big Bang never predicted this. Okay? All right, next slide. So they sent up a probe in the 1990 called the Kobe probe. Well, let's make sure that this is right, because we just saw it through telescopes before. Let's send up a probe out in space without any atmospheric distortion or anything to get in the way, and let's see what it finds. So here's what it came back with. Okay, same thing. Now this is the Milky Way getting in the way, so don't worry about that. But look how lumpy that is. Okay, so they had a problem. Not only was this microwave energy lumpy, but it was lumpy around the Earth. In other words, the lumpiness was only in certain pockets. So let's say this is the 23.5 degree axis that we all know about from the heliocentric view, right? Okay? So what they found was that the lumpiness, there would be a lump here and a lump there, and a lump here, a lump there, and a lump here, and a lump there, all the way to the edge of the universe. And then on the other side too. There's a lump here, a lump there, a lump here, a lump there. So what would that tell you if you were an astronomer? Yeah, the whole universe is aligned with the Earth. The ecliptic of the Earth. 23.5 degree tilt. Okay? The whole universe. You know what that's like saying? That's like saying that a pea is what is aligning the Milky Way. Because that's a big universe out there. And yet that's what they found. So they're scratching their heads. So not only is this stuff refuting the Big Bang, it now shows the Earth is what? Back in the center of the universe again. Remember Hubble tried to get it out with his balloon? Well, the microwave energy put it right back. So God's knocking on the door again. Yeah, you managed to escape that Big Bang stuff, huh? With your excuse. Okay? And now I'm coming back, knocking on the door. Here's this microwave energy. How are you going to explain that? Okay? So they sent up another probe. In 2001, let's keep going, called the WMAP probe, Wilkinson Microwave Anisotropy Probe, in case you want to know. And what did it come back with? Do those pictures look similar? Yeah. Here's a spot, there's a spot. Here's a spot, there's a spot. Here's a spot, there's a spot. It's identical. And this had more sophisticated instruments, less likely to have any error, and that's what it came back with. But in more detail now. Okay? So they were stuck. So then all the magazines started to come out with, the Earth is in the center of the universe. I could show you the magazine clips. They're all on the DVD. You can see them yourself. Major scientists of the world saying that the Earth is in the center of the universe. The universe is aligned with the Earth. Blah, 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 all kinds of titles. And you know what they called it? In 2004, there was a paper written, and they called it the axis of evil. Yeah, remember that axis I told you about? That 23.5 degree tilt with the lumps on either side of it, all the way to the edge of the universe? They called that the axis of evil. And they got that from President Bush when he was in Iraq in 2004, fighting the axis of evil. Okay, so that was a natural title to use. The axis of evil. Well, why is it evil for them? Because it totally defies the Copernican principle. Totally defies it. Because there shouldn't be any directions in space, especially not one that goes from one edge of the universe to the other, right through the Earth. Can't have that. Okay, next slide. And this is more technical stuff. I won't tell. Oh, okay. Okay. Here's another problem. You had these two axes here, and this is the one I just told you about. Okay, that tilt there, 23.5 degree tilt. Okay, then they found another one. another axial arrangement with the microwave radiation. And guess what this one did? This one went right through the equator of the Earth. Okay? Lump here, lump here, lump here, lump here, okay? And they call that the dipole, because basically there were two big poles, one over here that was blue, one over here that was red. And if you put it in the center of this dipole and the center of this one, and it would go right through the Earth's equator, or what they call the equinoxes. Okay? So now you had two directions in space that goes from one edge of the universe to the other. One on the Earth's equator and one on the Earth's ecliptic. So that's like an X. How much more perfect of a design of the center can you get than having the Earth right in the X, the middle of the X of the whole universe? Okay? All right, so next slide. Next slide. Here's a magazine article in 2007, Astronomy Magazine says, why is the solar system cosmically aligned? Okay? Well, that's another way of saying, why does the Earth look like it's in the center of the universe? Okay? But he changed the title a little bit. Let's put solar system in there so we don't shake people up. Okay? But it's really the Earth that he's talking about. This guy's in our movie, Max Tegmark, physicist from MIT. He basically changed his mind during the movie. He told us, I don't have an answer for you. See, we got him right after he saw the WMAP probe and its results. We interviewed him at MIT. He says, well, there might be a mistake here with this WMAP probe. I mean, I know what it says. It looks like that the solar system is aligned with the universe. I just don't want to make a decision yet. And then, just when we were about to close up the movie in production, the European Space Agency, in cooperation with NASA, came back with another probe that they'd sent up in 2009, and the results came back in 2013. And the results were exactly the same as the two previous probes. The COBE probe in 1990 and the WMAP probe in 2001. And so we interviewed Dr. Tegmark after the Planck probe results were released, and he said, yeah, I have to admit to you, I was rather bothered that the microwave is aligned with our solar system. I was very bothered about that, but I have to go by my brain and not my guts. I can't deny it. That's what he says in the movie. Okay? This is an MIT. This is one of the greatest astrophysicists in the world today. Okay? Admitting it right on camera. All right. Here's another guy, Dr. Lawrence Krauss, Arizona University. Check this out. But when you look at the CMB map, now the CMB map is the cosmic microwave background radiation. Okay? I just told you about. Okay? You also see that the structure that is observed is, in fact, in a weird way, correlated with the plane of the Earth around the Sun, the 23.5 degree tilt. Is this Copernicus coming back to haunt us? That's crazy. We're looking out at the whole universe. There's no way there should be a correlation of structure with our motion of the Earth around the Sun. Now remember, he's a heliocentrist, okay? The plane of the Earth around the Sun, the ecliptic, that would say we are truly the center of the universe. One of the most famous physicists in the world today, Lawrence Krauss. Okay? So like I said to you, I'm not making this stuff up. I'm just bringing it to you. Okay? These are the guys, the physicists who are saying it today. All right? So I think that's all we have time for tonight, and I'll take some questions now for, 15 minutes or so, and then we'll have to wrap it up.